Hello, welcome to Chemistry with Dr. Clark. Today we would like to talk about specific heat capacity problems. And the equation that we're going to be using for these is Q equals mc delta T. In this equation, the Q represents heat. It is always written as a lowercase q. The m stands for mass. The lowercase c is your specific heat capacity. In some textbooks and some problems, they shorten the name to just specific heat, so you have to watch out for that. Sometimes it's specific heat capacity, sometimes it's just specific heat. And the delta T is the change in temperature. It's calculated by taking the final temperature and subtracting off the initial. Now, in the problems that we're going to be working on, sometimes you'll have to do that subtraction yourself. You'll have to do the final minus the initial. In some problems, though, they will give it to you as delta T. They'll just give it to you as the change, right? The temperature went up by 10 degrees or the temperature went down by 15 degrees. So you do have to watch because sometimes you have to calculate it and sometimes you don't. Now, if you're doing these problems, my suggestion is memorize the formula and memorize what the unit goes with what quantity. Like when you see a mass, you should think that's an M. If you have the problem say the specific heat capacity is, then you should know right away that that's a C. You have to know the link between the symbols and the words. The other important thing here is the units. These problems can use a variety of units. The trick is that they have to match. So if you're going to measure your heats in joules and your masses in grams and your temperature in degrees Celsius, that's pretty standard because those would be SI units. Then your specific heat capacity is going to be measured in joules per gram degrees Celsius. Okay, it's a bit of a combination of units. But now you don't have to use these. If you've decided that you're going to go with kilojoules, grams and degrees Celsius, that's okay. But it means that your specific heat capacity has to be in kilojoules per gram degrees Celsius. Right? When you pick your units for these three, or the problem gives you units for these three, then it really does tie your hands in what units you're going to have over here. Now, more likely, you will be given this one, and this will determine the units that you'll use for everything else. So if your specific heat capacity is, say, given in calories per kilogram degrees Celsius, well, then your heat is going to have to be in calories, right? Heat can be measured in joules or kilojoules or calories or kilocalories. There's a variety. Your mass is going to be measured in kilograms rather than just grams. And your temperature is still in degrees Celsius. For these, the temperature doesn't usually change a whole lot. Degrees Celsius seems to be the one we like. For masses, sometimes we will use kilograms, but mostly we'll use grams. And for the heats, like I say, you can have joules, which is our favorite, or kilojoules, or calories, or kilocalories, right? There are a variety of units. The important thing here is consistency. Whatever unit you have in heat is also going to show up in your specific heat capacity. Whatever unit you have for temperature will also show up in your specific heat capacity. All right, let's try a couple of problems. So for the first problem, it says, how much heat energy in joules, okay, so they're telling me the units they want, is absorbed when 88 grams of water is heated from 5 degrees Celsius to 37 degrees Celsius. And the specific heat capacity of water is 4.18 joules per gram degrees Celsius. Now, if you are doing mixed problems, so you'll have heat capacity problems and you'll have, say, thermochemistry problems and you'll have heating and cooling curve problems, the problem is often choosing the approach. Like, what type of problem do I have? How to identify which formula to use? How am I going to approach this? For the heat problems, anything that involves a heat, if there is a temperature change, right, you're going from 5 degrees to 37, the minute that you have a temperature change, that's telling you that you're going to use Q equals mc delta T, right? The minute that you have a starting temperature and a finishing temperature, that's the calculation you have to use. Now, my suggestion, because I do like to keep myself organized, is if I'm using this formula, I'm going to write those 5 variables down off to the side. And I say 5 because temperature really is T final minus T initial. And so that way I can identify which numbers I have and which ones I'm looking for. So if I'm looking at this, it's saying how much heat energy. Okay, the key word here is the heat. I'm looking for the amount of heat, and the symbol for heat is Q. So that's going to be my question mark. That's what I'm looking for. It tells me that I have 88.0 grams of water. Now, the problem doesn't tell me if that's a temperature or a mass or a specific heat capacity, right? It doesn't identify it. But the minute that you see grams at the end, grams is an indicator of mass. So my mass is going to be 88 grams. The water is going to be heated from 5 to 37. So this is where I'm starting, that's my initial, and this is where I'm ending, that's my final. So my temperature is going to go to 37 degrees, that's my final. And where did I start? I started at 5. So my temperature went from 5 up to 37. Whoops, forgot my 0.0. And so if I do the subtraction, I get a change of 32 degrees. And if you think of it like on a nice summer's day, you wake up in the morning, it's 5 degrees, the temperature goes up to 37. How much did it change by? It changed by 32. Now the last thing is that it says the specific heat capacity of water is. So it gives you the C, 4.18 joules, grams, degrees Celsius. Now if I look at my units, they're matching up. See, I have a grams here in my mass, and I got a grams in my specific heat capacity. I've got a Celsius in my specific heat capacity. I've got a Celsius in my temperature. I've got a joules in my C, which tells me that when I calculate my heat, it's also going to be in joules, which is good because the question asked me for that. Now that I have all of my numbers, it's just a matter of substituting them into my equation and doing the math. So you don't know your Q, leave it as a Q. You do know your mass, that's 88.0. You do know your C, that's 4.18. And you do know your delta T, which is 32.0. Now this is a very nice problem because there's no rearranging. I just need to take my calculator and multiply them out. So 88 times 4.18 times 32 would give me, ooh, that's really big. I should check it again. 88 times 4.18 times 32. It is a big number. 11770.88. Now you'll notice that I didn't carry any of my units through my equation. Sometimes the person that's asking you to do the problems will want you to write the units in and cancel out anything that appears in both numerators and denominators. But when I looked at all of my units in the beginning, I know that they're all matching, and I know that my heat is measured in joules or calories or kilocalories or kilojoules. Based on what my C was, I knew that it had to be joules. So my answer will be in joules. Now, if significant figures are a part of your life, let's talk Sig Figs. So for this problem here, when I did the subtraction between 37.0 and 5.0, significant figures in subtraction is all about decimal places. So if I've got 1 decimal place here and 1 decimal place here, my answer should have 1 decimal place. When we talk about multiplying, it's all about the least number of Sig Figs. So 88.0 has 3 significant figures, 4.18 has 3 significant figures, and 32.0 has 3 significant figures. So my answer should only have 3 significant figures. So I can keep the 1, I can keep the 1, I can keep the 7, but really everything past that needs to go away. So to do this, I really should write it in scientific notation. So this is going to be 1.17788 times 10. Now, if I've moved the decimal place to here, I've moved it 1, 2, 3, 4 times. So that's 10 to the power of 4 joules. Right, I just moved my decimal place 4 times, so it became times 10 to the power of 4. Now that it's in scientific notation, now it's easy for me to round it off. Right, so when I round this thing, it's going to become 1.18. Right, if I'm getting rid of that 7, I have to round up, times 10 to the 4 joules. Now this is kind of the standard problem. When we're doing science, we do tend to see 3 sig figs in numbers, right? 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. It doesn't always work that way, but it often does tend to play out that way. All right, so let's try a second problem. It says a piece of gold weighing 35 grams absorbs 185 joules of heat. Its temperature increases by 41 degrees. Calculate the specific heat capacity of gold. Now again, it's talking about a temperature change, right? The temperature is increasing by 41. Now they're trying to help me here. Instead of making me calculate the delta T, they've already done it for me, right? This is the change in the temperature. I don't know what the initial was. I don't know what the final was, but I do know the change. And the minute you have a change in temperature, you know that you're using Q equals mc delta T. So again, let's write out our variables. Q, M, C, delta T. So it says a piece of gold weighing 35 grams. The minute I see grams, I know it's a mass, and mass has symbol of M. So M is 35.0 grams. It says it absorbs 185 joules of heat. Well, it's telling me that it's heat, and I know the symbol for heat is Q. But also, if I look at the units and see that it's a joules, joules is a unit for heat, right? So that also tells me that it should be the Q, 185 joules. It tells me the temperature is going up by 41 degrees, so that's my delta T. And it's looking for the specific heat capacity of gold. We're looking for this number. Now, I can make a prediction of what the units are going to be right off the top, because I know that the units are always heat on the top, mass and temperature on the bottom. So if I've got a joules, I know it's going to be joules per gram degree Celsius, which turns out to be one of our favorite sets of units. Now this problem will require a little bit of rearrangement. You can either put your numbers in first and rearrange it, or you can rearrange it first and then put your numbers in. Let's say that we want to rearrange first. So if I'm going to solve for C, I need to move everything else to the other side. So if the M is multiplied and the delta T is multiplied, when I move them to the other side, they move through division. So this will be Q divided by M divided by delta T equals my C. Now, even though I know what the units are, let's put all of the units in and see what happens. So if I put in my value for Q, that's 185 joules. If I put in my value for M, that's 35.0 grams. And if I put in my value for delta T, that's 41.0 degrees Celsius. So again, if we pull out our calculator. Now you do have to be careful if you're dividing by two numbers on the bottom. You're either going to have to use brackets, or really, my 185 is divided by the 35, but it's also divided by the 41. So I can say 185 divided by 35 divided by 41. So it gives me an answer of 0.1289. And now the reason why I wanted to leave all the units in is because you can see it gives me the right ones. I've got joules on the top. I got grams and degrees Celsius on the bottom. So grams, degrees Celsius. And that's my C. If you are a significant figure person, you can see that again, this is one of our classic cases. 185 has 3 sig figs. 35.0 has 3 sig figs. 41.0 has 3 sig figs. So my answer should only have 3. Now you do have to be careful. This 0 out in front doesn't count Because really, if I wanted to, I could have wrote it as just 0.1289, and you would have known exactly what I meant. Okay, so that one doesn't count. So if I'm counting out 3, that'll be the 1, the 2, the 8, and I'm going to chop off the 9. Now, if you're going to chop off a 9, that means you round up. So my answer will become 0.129 joules grams degrees Celsius. All right, let's try another one. It says, when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85. What is the specific heat capacity of olive oil? Now, it turns out that this problem really is the same as this one, but you've got to do a bit more work, right? For this one here, they're telling you the initial and the final temperatures, so you've got to work for the delta T. But this problem asks for specific heat capacity. This problem is also asking for it, so really it's the same thing. Again, the minute you see the temperature change, you're going to be using Q equals MC delta T. List my variables. Q, M, C, delta T. T final minus T initial. So you've got 435 joules of heat. The joules tells you it's heat. The word heat tells you that it's heat. So that's your symbol Q. 435 joules. The 3.4 is in grams. Grams are a mass, so that's your symbol M, 3.4 grams. And your temperature is going to start at 21, and it's going to go up to 85. So this one's your initial, this one's your final. So if we're going to do our delta T, 85 is my final, 21 is where I started. And if we subtract that, that gives me 64 degrees. And it does say what is the specific heat capacity of the olive oil, and we know the symbol for specific heat capacity is C. Now, once again, I know what the units of this are going to be, right? I've started with joules, I've got some grams, I've got some degrees Celsius. So I know that it's going to be joules over grams degrees Celsius, right? I know what it's going to be. Now again, you are looking for the C, so perhaps we'll rearrange first, right? If you're multiplying by the M and the delta T, you move it through the other side through division. So Q over M delta T equals my C. So put in your numbers. 435 divided by your mass, which was 3.4, divided by your delta T, which was 64. Again, you're dividing by two separate numbers, so you can do the division twice. So 435 divided by 3.4 divided by 64 gives me 1.99999. Okay, so 1.999. You will notice this time I didn't bother to put my units in because I am very confident at what they should be. So you can either put them in or not, right, as long as you have them at the end. Or, depends on whoever's asking you to do the problem. If they want you to put the units in all the way through, then you have to put the units in all the way through. Now, if we do talk significant figures for this one, the significant figures are a little bit less nice than the early ones, right? Everything else we've done so far have had 3. If you look at this, though, the Q has 3, the mass only has 2, and the temperature has only 2. So when I do my answer should only have 2. So I can keep the 1, I can keep the 9, but I got to get rid of everything else. And if I'm getting rid of a 9, that rounds up. So 1.9 would round to 2.0 joules grams degrees Celsius. Okay, let's try another one. Let's say that we take a look at number 4. Number 4 here has a little bit of a twist to it. It's saying how much heat is needed to raise the temperature of 0.250 kilograms of mercury by 52 degrees Celsius, the specific heat capacity is. Now, it is telling us about a change in temperature. So if you have a change in temperature, you know what formula you're using. Q equals mc delta T. If we list our variables, Q, M, C, delta T, let's fill in what we know. It says how much heat has a symbol of Q, is needed to raise the temperature of 0.25 kilograms. Now, if you've got kilograms, you know that's a mass. It is a little bit different from normal because everything else we've done has been in grams. But like I said in the very beginning, you're able to go with kilograms as long as all the units match up. Now, it says that the temperature is going to go up by 52 degrees. This problem is attempting to make your life a little easier. Instead of giving you an initial and a final, they're telling you a change. So it'll be 52 degrees. And they do say the specific heat capacity of mercury is 0.139 joules grams degrees Celsius. Okay, so it looks like a nice problem. Basically, you've got these three variables, so you're just going to put them in, multiply them together, and you're done. The issue, though, is that your units don't match. Here you've got a grams. We love grams. Here we got a kilograms. We also love kilograms, but we don't love them in the same problem. So for this one here, you are going to have to change one of them. You can change them both the kilograms, you can change them both the grams. Probably the easiest thing to do is to turn this one into a grams. And we know if you want to turn kilograms into grams, you have to multiply by 1,000. So 0.250 kilograms would give you 250 grams. Now my units match up. Okay, that's the only thing in this problem that made it a little bit harder than the rest. So let's throw our numbers in. The mass, I know the mass. It's 250 grams. The C, I know the C, 0.139 joules grams degrees Celsius. And I know the delta T, 52.0 degrees Celsius. Now, the last time that I did a problem like this, I left all the units out and I just kind of stole one from the end. But if you do have to cancel, any unit that appears in both a numerator and a denominator cancels. So this is a grams in a numerator. This is a per gram in the denominator. So they cancel. This is a degree Celsius in the denominator. This is a degree Celsius in the numerator. They cancel. And so the only unit you have left is joules, which is not surprising because we know that heats are measured in joules and kilojoules and that it has to match. So if this one here has joules, I really did anticipate that this would end up in joules as well. Okay, so let's multiply those things out. 250 times 0.139 times 52 gives me 1,807. So Q is 1,807, and the only unit left is my joules. If you are going to do significant figures, 3 Sig Figs, because remember the 0 in front don't count, and 3 Sig Figs. So this thing should only have 3 significant figures. It's really hard to get rid of the 7 because you kind of need it to be 1,800. So what I'm going to do is write it in scientific notation. So I'm going to call it 1.807, and I've moved the decimal place 1, 2, 3 times. So times 10 to the power of 3 joules. Because if I write it in scientific notation, then I can say 1 Sig Fig, 2 Sig Figs, 3 Sig Figs, and I can actually chop off that last one. Right? Because it's very easy to cut off trailing decimal points. So if I get rid of the 7, that rounds it up, and I get 1.81 times 10 to the power of 3 joules. Basically 1,800 joules. All right, let's get to the last problem here, and these two are linked together. For the first one, it's just kind of a normal thing. It says how many joules are required to heat up 100 grams of copper. They give the specific heat capacity from 10 to 100. It's the same as this problem here, right? It's the same as problem number 1. It's just they give you the numbers, you put them in, you calculate the Q. So if we breeze through it kind of quickly, Q equals mc delta T, Q mc delta T, which is T final minus T initial. So if they're looking for joules, that's the heat. There's my question mark. They tell me 100 grams, so that's my mass. And the problem tells me my specific heat capacity. 0.385 joules, grams, degrees Celsius. And it says the temperature goes from 10 to 100. Initial, final. So my delta T will be 100 minus 10, which gives me a 90-degree change. Whoops, don't forget my 0.0 degrees Celsius, right? Because if you're subtracting, if this has 1 decimal place, this has 1 decimal place, so your answer should have 1 decimal place. All right, now if we look at our units, grams and grams, degrees Celsius and degrees Celsius, since this is a joules, I would anticipate that that's also going to be a joules. So let's put our numbers in. Mass of 100, C of 0.385, and a delta T of 90. So my Q will end up being 100 times 0.385 times 90. So that's 3,465 joules. If you are doing significant figures, the 100.0 has 4. The 0.385, remember 0 in the front don't count, so it has 3. And this has 3. So really, this should be cut off here at 3 sig figs, right? So I'd have to put it in scientific notation. 465 times 10 to the 3 joules. Right, you move your decimal place 3 times. And you want 3 sig figs. So the 3, the 4, the 6, get rid of the 5. So it rounds up. That'll give me 3.47 times 10 to the 3 joules as an answer. Now, often in these problems, what they want to do is they'll give you an A, get you to find an answer, and then in the B, you have to link it to something else. So in B, they're saying, hey, instead of using copper, we're going to use aluminum. But we are going to use the exact same amount of heat. So the amount of heat that you calculated here is going to be the amount of heat in the second problem. They're going to keep the mass the same. You've still got 100 grams. They're going to keep the starting temperature the same. You're starting at 10 degrees. But they want to know which one's going to get hotter. They would like to know if you have the same heat and the same mass, but different specific heat capacities, what effect does that have on the final temperature? Okay, so now this problem is a bit different. We have never really calculated temperature changes, right? We've always had the temperature change, but we've never really been looking for it, right? In this problem, that's what we're looking for. So again, the problem is talking temperature change, so we only got one formula, Q equals mc delta T. List our variables, Q, M, C, delta T, which will be our question mark. So the problem says you're using the same amount of heat. So we're going to use 3,465 joules. Now, just to make my life easier, instead of using the scientific notation, I'm just going to go back to the original number. But I have to keep in my mind that when I'm doing sig figs, that this, even though it looks like it has 4, really should only have 3. Okay, so I chose that to make my calculation life happier, but I got to keep in mind that that really is only 3 significant figures. Now, it does say that the mass is going to be the same, which is 100 grams. The specific heat capacity is 0.908 joules, grams, degrees Celsius. And I am looking for the temperature change. Okay, so let's put our numbers in. This is 3,465. The mass is 100. The C is 0.908. And a delta T. Now, in earlier problems, when I had to rearrange, I rearranged the equation first and substituted second. You could have done that here, right? You could have moved the m over and the c over. Sometimes, though, I just like to put my numbers in first and work through them. So this would be 3465. 100 times 0.908 gives me 90.8 times delta t. And if these two are multiplied, to get rid of it, I'm going to divide it off both sides. So 90.8. So that'll give me 3465 divided by 90.8, 3816. So 38.16 degrees Celsius is my delta t. Now, a couple of things. Let's do Sig Figs. 0.908 has 3 Sig Figs. The 100, oops, I left out my 0.0, that was sloppy, has 4 Sig Figs. And the 3465, even though I have it written with 4, should only have 3. So 3 Sig Figs, 4 Sig Figs, 3 Sig Figs. The answer has the least, which would be 3. So the 38.16 should be rounded off just to 3 Sig Figs. So that'll give me 38.2. Now, that's not a final temperature. That's the temperature change. So if you have started at 10 degrees and the temperature goes up by 38, your final temperature is the initial temperature plus your delta T. Right? Where you started plus how much you changed by. So if you started at 10 and you went up by 38, your final temperature is 48.2. Right? Because start at 10, add 38. Now, these two problems are nice problems by themselves, but they're put together to show you something bigger. The specific heat capacity of copper is pretty small. 0.3 is pretty small. The specific heat capacity of aluminum at 0.9 is much bigger. It's like almost 3 times as big, more than double. If you have a really small specific heat capacity, that means it's really easy to heat up. It's like a cost, right? You go into a store and something costs you like 38 cents. That's really cheap to buy. If you're going to the store and you buy something at 0.90 cents, right? 90 cents, that's more expensive. You can buy more cheap things with your $5 than you can buy expensive things with your $5, right? That's how specific heat capacities work. It's like the cost to heat something up. So if the cost is low, then it heats up really fast, right? It went from 10 all the way up to 100 degrees, right? It went up by 90 degrees. This one here has a much higher heat capacity, which means it's more expensive to heat it. Like you have to put in a lot more heat before the temperature goes up. And so because it's harder to heat, even though you put in the same amount of heat, you didn't get as much temperature change, right? It only went from 10 to 48 rather than 10 to 100. So that's part of what that problem wanted to show you, is that things with really high specific heat capacities, you can put in a lot of heat, but they're not going to heat up a lot. You have things with really low specific heat capacities. If you put in a lot of heat, then they are going to heat up quite a bit. So I hope this helps you in your working on your specific heat capacity problems. If you are looking for help with any other thermodynamic questions, heating and cooling curves, thermochemical equations, those sorts of things, please check out some of the other videos. Once again, I'm Dr. Clark.